we will study the dual nature of radiation. The wave nature of light was established by Maxwell's and Hertz in 1887, followed by the experimental investigations on conduction of electricity through gases at low pressure. The discovery of X-rays by Roentgen in 1895 and electron by J. Thomson in 1897 were important milestones in understanding of atomic structure. Around 1887, it was found that certain metals, when irradiated by ultraviolet light, emitted negatively charged particles having small speeds. Also, certain metals, when heated to high temperature, were found to emit negatively charged particles. The value of E by m of these particles was found to be the same as that of cathode ray particles. These observations thus established that all these particles, although produced under different conditions, were identical in nature. J. Thomson named these particles as electrons and suggested that they were fundamental and universal constituents of matter. For this epoch-making discovery of electrons through his theoretical and experimental investigations on conduction of electricity by gases, he was awarded Nobel Prize in Physics in 1906. In this chapter, we will study the theory of electron emission, photoelectricity, particle nature of light and wave nature of matter. So, I welcome you for this session. Please note down all important points which will be helpful for you in the examination. Welcome once again. Electron emission. The elementary particle in an atom having a negative charge of magnitude 1.6 into 10 to the power of minus 19 coulomb and mass of 9.1 into 10 to the power of minus 31 kgs is called electron. Free electrons in metals are responsible for electrical conduction. Electrons are negatively charged particles having charge to mass ratio, that is E by m is equal to 1.6 into 10 to the power of 11 coulombs per kg. Normally, the free electrons cannot escape from metal due to acquisition of positive charge at the surface of the metal. Thus, the free electrons are held inside by the attractive forces of positive ions of the metal. A certain minimum amount of energy is required to pull out electrons from metal surface. This minimum energy required by electrons to escape from the metal surface is called work function of the metal. It is denoted by letter phi naught and measured in electrons volt, that is electron volt. 1 electron volt is the energy gained by an electron when it is accelerated by a potential difference of 1 volt. So that 1 electron volt is equal to 1.602 into 10 to the power of minus 19 joules. The unit of energy is commonly used in atomic and nuclear physics. The work function phi naught depends on the properties of metal and nature of its surface. Now, let us study about work function of certain metals. Please see the table shown before you. The first column contains the names of the metal and the second column work function phi naught in electron volts. For calcium Cs, the work function is 2.14. For potassium it is 2.3. For sodium, whose symbol is Na, the value of work function is 2.75 electron volts. For calcium, it is 3.2 electron volts. For molybdenum, work function phi naught equals 4.17. For lead, it is 4.75. For other metals like aluminum, the work function is 4.28. For mercury, it is 4.49. For copper, work function is 4.65. Silver, it is 4.7. Nickel, it is 5.15. And platinum, it is 5.65. That means we have to apply a work function of about 5.65 electron volts to platinum for the electrons to come out of its metal surface. Electron emission processes. The minimum energy required for electron emission can be supplied to free the electrons by any one of the following processes. Thermionic emission. By suitably heating, thermal energy can be imparted to the free electrons to enable them to come out of the metals. That means if you heat the metals, electrons will gain energy and they will come out of the internal surface, metal surfaces. Field emission. By applying a very strong field of the order of 10 to the power of 8 volts per meter to a metal, electrons can be pulled out of the metal, as in the case of a spark plug. Photoelectric emission. When a light of suitable frequency illuminates a suitable surface, electrons are emitted from the metal surface. These photo or light generated electrons are called photoelectrons. Hence, there are three methods or three processes by which electrons come out of their respective metals and contribute for conduction. First process is thermionic emission. That means it is to be heated. By heating, the thermal energy can be imparted to the free electrons and they come out of the metals. Similarly, second process is field emission. By applying a very strong electric field to the metal, electrons can be pulled out of the metal. And the third process is photoelectric emission, in which light of suitable frequency, please note suitable frequency, illuminates a suitable surface and electrons are emitted from the metal surface. These photo generated electrons are called photoelectrons. Photoelectric emission. Photons. Photons are the packets of energy emitted by a source of radiation. Photons are packets of energy emitted by a source of radiation. The energy of each photon is represented by E is equal to h nu, where h is the Planck's constant and nu is the frequency of radiation. Properties of photons. A photon travels at a speed of light c in vacuum. That is, its speed is 3 into 10 to the power of minus 8 meters per second. It has zero rest mass, that is, photon cannot exist at rest. So, photon is always moving. Dynamic or kinetic mass of photon is m is equal to h nu divided by c square or h divided by c lambda. where h is the Planck's constant, nu is the frequency, c is the velocity of light, and lambda is the wavelength. Momentum of photon. Momentum of photon is represented by letter P, and it is given by P is equal to h nu by c, that is equal to h lambda. Photons travel in a straight line. Point number 6. Energy of photon depends on frequency of photon. So, the energy of photon does not change when photon travels from one medium to another. Only when frequency changes, the energy will change. Wavelength of photon changes in different media. So, the velocity of photon is different in different media. Photons are electrically neutral. Photons may show diffraction under given conditions. Photons are not deviated by magnetic and electric fields. Figure shows a schematic arrangement for study of the photoelectric effect. It consists of an evacuated glass or oblique quartz tube having a photosensitive plate C and another metal plate A. Monochromatic light from source S of sufficiently short wavelength passes through the window W and falls on the sensitive plate C, which is also called collector. Electrons, if there is another plate A which is called collector. If A is kept positive due to a battery potential here, the electrons are attracted towards it and a current flows in the circuit. This current is measured through a microammeter, and the potential difference between A and C is measured. The commutator helps us to reverse the polarity. That is, earlier if it was A, then by reversing the commutator we can make A as the negative, as well as we can vary the potential difference applied to A. The intensity and frequency of incident light can also be varied. Light of different frequencies can be used by putting appropriate colored filter between S and C. The intensity of light is varied by changing the distance between S and C. Different parts of the circuit setup are also explained in the legend. Keeping the frequency in the first curve, keeping the frequency constant and potential difference fixed, the intensity of light is varied and the resulting photoelectric current is measured each time. It is found that the photocurrent increases linearly with intensity of incident light as shown graphically in the figure. The photocurrent is directly proportional to the number of electrons emitted per second, which in turn is directly proportional to the intensity of incident radiation. Now, in the second graph, we vary the positive potential of plate A gradually and measure the resulting photo current each time. That means we keep intensity I1 constant and vary the potential, collector potential. We find that the photoelectric current increases and with the increase in positive potential till the photoelectric current becomes maximum or saturated. Here the current saturates here. This saturated, if we further increase the accelerating potential, there is no increase in the current. This maximum value of photoelectric current is called saturation current. Saturation current corresponds to the case when all the photoelectrons emitted by the emitter plate C reach the collector plate A. Now we reverse the potential here. We make it, till now it was positive. Now we reverse it in the negative. We now apply a negative or a retarding potential to the plate A with respect to plate C. When the polarity is reversed, the electrons are repelled and the only most energetic electrons are able to reach the collector A. The photo current is found to decrease rapidly until it drops to 0. This minimum negative potential V0 given to plate A, for which photocurrent stops or becomes 0, is called the cutoff or the stopping potential. Here you see the photocurrent is 0 and the voltage, potential voltage is minus V0. This voltage at which the photocurrent stops is called the stopping potential. We can repeat this experiment for different values of intensity. Let us take the case of I2. I2 greater than I1. So, I2 has got another saturation current here, which is higher than I1, the saturation current of I1, and again, but V0 is same, that is stopping potential is same for the curves with different values of intensities. Third curve also is for the intensity I3. I3 is greater than I2 and I1, but stopping potential is same. Now let us take the third case. Here we maintained, in the previous case we varied the intensities I1, I2, I3, but in this case we keep the intensity same, we do not change the intensity, but we vary the frequency. For different frequencies we find, say take for example frequency nu1. For nu1 we find the saturation current is same, whereas the retarding potential is V0. So, for V1 the retarding potential is V0. So, we again we repeat the experiment for a different frequency equal to nu2. For nu2 we find that the retarding potential is minus V0. As we increase the collector potential, the saturation current also joins and merges with the previous curve, indicating that saturation current is same for different frequencies. It does not change with frequency, but retarding potential has increased from minus V0 in the previous case to the present case minus V02. And again we can repeat for yet another frequency nu3. For nu3 the retarding potential is minus V03, whereas the saturation current is same. This is the curve for photoelectric current versus potential for different frequencies. The frequencies are varied. Here different intensities. Now this can also be replotted as a frequency of incident radiation nu versus stopping potential. Stopping potential is plotted here. For any particular material A, metal A, there is a threshold frequency nu naught, below which there is no current. Current is 0. It remains 0. Current remains 0, and after reaching V0, it increases. Hence, here V is greater than V0 and below V0 there is no current. If we change the metal of the emitter plate C, we get another value. For a metal B, the threshold frequency is V0 dash. So, it is a function of the material. Hence, we have plotted here stopping potential versus frequency of incident radiation. Now, the observations can be summarized as follows. The photoelectric current is directly proportional to the intensity of incident light for a given photosensitive material and frequency of incident radiation above the threshold frequency. The photocurrent is directly proportional to the intensity of light. The saturation current is found to be proportional to the intensity of radiation as in the case of graph number 2, whereas the stopping potential is independent of the its intensity. So, that is, if you keep the intensity same, vary the intensity, the stopping potential remains same. In the third case, there exists a certain minimum cutoff frequency of incident radiation called the threshold frequency, below which no emission of photoelectrons takes place. That is graph number 4. For a given photosensitive material, no matter how intense the incident light is, above the threshold frequency, the stopping potential or the equivalent, the maximum kinetic energy of the emitted photoelectrons increases linearly with the frequency of incident radiation, but it is independent of its intensity. There is yet another observation. The photoelectric emission is an instantaneous process without any apparent time lag or even when the incident radiation is made exceedingly dim. Photoelectric terminologies. Let us revise the terminologies used in study of photoelectric effects. Threshold frequency. As described in the earlier slide, the cutoff frequency of the incident light below which no emission of photoelectrons takes place from metal surface is called the threshold frequency. That is, it is the minimum frequency below which no emission will take place. Threshold wavelength. Lambda max, it is represented by symbol lambda max. The maximum wavelength of light which can eject photoelectrons from a metal surface is called the threshold wavelength of that metal. Relation between work function, threshold frequency and threshold wavelength. It is given by equation phi is equal to hc divided by lambda max, where phi is the work function equal to h is the Planck's constant, c is the velocity of light, and lambda max is the maximum wavelength of light which can eject photoelectrons from metal surface. Saturation current. For a given beam of incident radiation at certain value of accelerating potential, the photoelectric current becomes maximum, and this maximum value of photo current is saturation current. This is shown in graph number 2 of the previous slide, as well as graph number 3 also, saturation current. Stopping potential. For a particular frequency of incident radiation, the minimum negative potential V naught given to the collector plate, for which the photocurrent becomes 0 or cut off, is called the stopping potential or retarding potential. This is shown in graph number 2 and graph number 3 of the previous slide. Loss of photoelectric emission. For a given substance, there is a minimum value of frequency of incident light called threshold frequency, below which no photoelectric emission is possible, howsoever the intensity of incident light may be. This is the minimum value of frequency. Threshold frequency is the minimum value of frequency below which there is no emission of electrons. This is shown in figure number 4 of the previous slide. The number of photoelectrons emitted per second, that is the photoelectric current, is directly proportional to the intensity of incident light, provided the frequency is above the threshold frequency. That means intensity is directly proportional to the number of photoelectrons is directly proportional to the intensity of incident light. This is shown in figure number 1 of the graph number 1 of the previous slide. The maximum kinetic energy of photoelectrons is directly proportional to the frequency, provided the frequency is above the threshold frequency. That means the kinetic energy of photoelectrons is directly proportional to frequency when the frequency is above the threshold frequency. The first condition is the frequency should be above threshold frequency and kinetic energy is directly proportional to the frequency. This is shown in graph number 4 of the previous slide. The maximum kinetic energy of photoelectrons is independent of the intensity of incident light. Hence, this is shown in figure number 2, graph number 2, where it is plotted the photoelectric current versus the potential. The process of photoelectric emission is instantaneous. That is, as soon as the photon of suitable frequency falls on the substance, it emits photoelectrons. Number 6. The photoelectric emission is 1:1. That is, for every photon of suitable frequency, one electron is emitted. Energy quantum of radiation. The wave nature of light was very well established by the end of 19th century. The phenomena of interference, diffraction and polarization were explained in a natural and satisfactory way by the wave picture of light. According to this picture, light is an electromagnetic wave consisting of electric and magnetic field with continuous distribution of energy over a region of space over which the wave is extended. Let us now see if this wave picture of light can explain the observations on photoelectric emissions given in the previous slide. According to wave picture of light, the free electrons at the surface of metal over which the beam of radiation falls absorb the radiant energy continuously. The greater the intensity of radiation, the greater are the amplitudes of electric and magnetic fields. Consequently, the greater the intensity, the greater should be the energy absorbed by each electron. In this picture, the maximum kinetic energy of photoelectrons on the surface is then expected to increase with increase in intensity. Also, no matter what the frequency of radiation is, a sufficiently intense beam of radiation over sufficient time should be able to impart enough energy to the electrons so that they exceed the minimum energy needed to escape from the metal surface. A threshold frequency therefore should not exist. These expectations of wave theory directly contradict the observations made in the previous slide 11.5 and 11.6. Since large number of electrons absorb energy, the energy absorbed per electron per unit time turns out to be small. Explicit calculations estimate that it can take hours or more for a single electron to pick up sufficient energy to overcome the work function and come out of the metal. This conclusion is again in striking contrast to observation number 4 in slide number 11.5 and 11.6 that the photoelectric emission is instantaneous. In short, the wave picture is unable to explain the most basic features of photoelectric emission. When a photon of energy hV falls on a metal surface, the energy of a photon is absorbed by the electron and is used in two ways. First, a part of this energy is used to overcome the surface barrier and come out of the metal surface. This part of energy is called work function, and work function is given by phi is equal to h nu naught. The remaining part of the energy is used in giving a velocity nu to the emitted photoelectron. This is equal to the maximum kinetic energy of photoelectrons. That is, this kinetic energy is half mv square maximum, V max square, where m is the mass of photoelectron. In 1905, Albert Einstein proposed a radically new picture of electromagnetic radiation to explain photoelectric effect. In this picture, the photoelectric emission does not take place by continuous absorption of energy from radiation. Radiation energy is built up of discrete units, the so-called quanta of energy radiation. Each quantum of radiant energy has energy h nu, where h is a Planck's constant and nu is the frequency of light. In photoelectric effect, an electron absorbs a quantum of energy h nu of the radiation. If this quantum of energy absorbed exceeds the minimum energy needed for the electron to escape from the metal surface, that is work function phi naught, the electron is emitted with maximum kinetic energy, and this is given by equation k max is equal to h nu minus phi naught. This is the equation, k max is equal to h nu minus phi naught. More tightly bound electrons will emerge with kinetic energies less than the maximum value. Note that the intensity of light of a given frequency is determined by the number of photons incident per second. Increasing the intensity will increase the number of emitted electrons per second. However, the maximum kinetic energy of photoelectrons is determined by the energy of each photon. Equation k max is equal to h nu minus phi naught is known as Einstein's photoelectric equation. We now see how this equation accounts in simple and elegant manner all the observations on the photoelectric effect. At the end of that previous section 11.5, according to equation Einstein's photoelectric equation, k max depends on nu and is independent of intensity of the radiation in agreement with the observation. This has happened because in Einstein picture the photoelectric effect arises from absorption of a single quantum of radiation by a single electron. The intensity of radiation, which is proportional to the number of energy quanta per unit area per unit time, is irrelevant to this basic process. Since k max must be non-negative, it implies that photoelectric emission is possible only if h is greater than phi naught, or nu should be greater than nu naught, where nu naught is equal to phi naught by h. Nu naught is equal to phi naught by h. This shows that greater the work function phi naught, the higher the minimum or threshold frequency nu naught needed to emit photoelectrons. Thus, there exists a threshold frequency nu naught equals to phi naught by h for metal surface, below which no photoelectric emission is possible, no matter how intense the incident radiation may be or how long it falls on the surface. In this picture, intensity of radiation, as noted above, is proportional to the number of energy quanta per unit area per unit time. The greater the number of energy quanta available, greater is the number of electrons absorbing the energy quanta, and greater therefore is the number of electrons coming out of the metal. This explains why for nu greater than nu naught, photoelectric current is proportional to the intensity. In Einstein's picture, the basic elementary process involved in photoelectric effect is absorption of a light quantum by an electron. This process is instantaneous. Thus, whatever may be the intensity, that is, the number of quanta of radiation per unit area per unit time, photoelectric emission is instantaneous. Low intensity does not mean delay in emission, since basic elementary process is the same. Intensity only determines how many electrons are able to participate in the elementary process, that is absorption of a light quantum by a single electron, and therefore the photoelectric current. Now these equations are given here. H nu should be greater than phi naught for emission. Therefore, but K max is given by electron volt E V naught, that is equal to H nu naught minus phi naught, that is Einstein's photoelectric equation. Then dividing by E, we get V naught is equal to H by E into V minus phi naught by E. This is the equation of a straight line. This explains the reason why the saturation potential obeys linearly, increases linearly with respect to frequency. K max is equal to Hv minus Hv naught, that is half mv square is equal to, this is K is a kinetic energy, half mv square, that is equal to H into V minus V naught. So, if V is greater than V naught, then emission takes place. This is an important result. It predicts that V naught versus V curve is a straight line with slope h by E, independent of the nature of the material. That is, h by E is the slope of the curve or the graph. During 1906-1916, Millikan performed a series of experiments on the photoelectric effect aimed at disproving Einstein's photoelectric equation. He measured the slope of the straight line obtained for sodium and similar to that shown in figures. The known value of E, he determined the value of Planck's constant. This value was close to value of Planck's constant, that is equal to 6.626 into 10 to the power of minus 34 joule seconds, determined entirely in a different context. In this way, in 1916, Millikan proved the validity of Einstein's photoelectric equation instead of disproving. He wanted to disprove the Einstein theory, but ultimately ended up proving the Einstein theory. The successful explanation of the photoelectric effect using the hypothesis of light quanta and the experimental determination of values of H and phi naught in agreement with the values obtained from other experiments led to the acceptance of Einstein's picture of photoelectric effect. Millikan verified photoelectric equation with great precision for a number of alkali metals over a wide range of radiation of frequencies. Now, let us verify the laws of photoelectric emission based on Einstein's photoelectric equation. Consider equation number 4, that is V is less than V naught, then half mv square is negative, which is not possible. If V naught is greater than V naught, then negative kinetic energy is not possible. Therefore, the photoelectric emission takes place only when V is greater than V naught. V naught is the threshold frequency. Since one photon emits one electron, so the number of photoelectrons emitted per second is directly proportional to the intensity of incident light. It is clear that half mv max square is proportional to V in this equation, is proportional to, as H and V naught are constants. This shows that kinetic energy of photoelectrons is directly proportional to the frequency of the incident light. So, kinetic energy is proportional to the frequency of the incident light. Equation 2, that is V naught is equal to h by E into V minus phi naught by E predicts that V naught versus V is a straight line with slope h by E independent of the nature of the material. Photoelectric emission is due to collision between a photon and an electron. As such, there cannot be any significant time lag between the incidence of photon and emission of photoelectron. That is, the process is instantaneous. It is found that delay is only 10 to the power of minus 8 or 10 to the power of minus 9 seconds. Particle nature of light. Summarized picture of photon of electromagnetic radiation. In interaction of radiation with matter, radiation behaves as if it is made up of particles of photons. Each photon has an energy E is equal to h nu and momentum P is equal to h nu by c. All photons of light of a particular frequency V or wavelength lambda have the same energy, that is E is equal to h nu, or that is also equal, can also be written as h c by lambda, and momentum P is equal to h nu by c or h by lambda, where c is equal to, c is the speed of light whatever the intensity of radiation may be. Photon energy is independent of intensity of radiation. Increase the intensity of light of a given wavelength increases only the number of photons. Photons are electrically neutral and are not detected by electric and magnetic field. The total energy of total momentum and the total momentum in photon particle collision are conserved. Applications of photoelectric effect. There are a number of applications of photoelectric effect. Let us quickly go through them. It is used in automatic fire alarm, automatic burglar alarm, scanners in TV transmission, reproduction of sound in cinema films, in paper industry to measure the thickness of paper, to locate flaws or holes in finished goods. Photoelectric effect is also used in astronomy. It is to determine the opacity of solids and liquids. Automatic switching of street lights. Number 10, to control the temperature of furnace. It is also used in photometry, that is measurement of photoelectricity. Beauty meter, to measure the fair complexion of skin. Light meters used in cinema industry to check the lights. Photoelectric sorting, photo counting and meteorology. These are the applications of photoelectric effect. Work examples. Find the maximum frequency and minimum wavelength of X-rays produced by 30 kV electrons. Given V is equal to 30 kV, that is equal to 30 into 10 to the power of 3 volts. We know h V max is equal to EV. Therefore, V max is equal to EV divided by h. We know the value of E is 1.6 into 10 to the power of 3 into 30 into 10 to the power of 3 divided by h. Planck's constant value is 6.63 into 10 to the power of minus 34. That is equal to 7.24 into 10 to the power of 18 hertz. Therefore, lambda minimum will be given by equation C by V max, that is equal to 3 into 10 to the power of 8 divided by 7.4 into 10 to the power of 18. That is equal to 0.0414 nanometers or 0.414 Armstrongs. Example 2. The photoelectric cutoff voltage in a certain experiment is 1.5 volt. What is the maximum kinetic energy of photoelectrons emitted? Solution. V naught is equal to 1.5 volts. It is given. Therefore, K max is equal to V naught. K max is equal to E into V naught. That is equal to 1.6 into 10 to the power of minus 19. That is the charge E, value of E into 1.5 volts. That is given. And simplifying, calculating, we get 2.4 into 10 to the power of minus 19 joules. Example 3. The monochromatic light of wavelength of 632.8 nanometer is produced by helium neon laser. The power emitted is 9.42 milliwatts. Find the energy and momentum of each photon in the light beam. How many photons per second on the average arrive at the target irradiated by this beam? Assume the beam to have a uniform cross section which is less than the target area, and see how fast does a hydrogen atom have to travel in order to have the same momentum as that of photon. Given lambda is equal to 6.32.8 nanometer. That is equal to, nano means we have to multiply with 10 to the power of minus 9. That is equal to 6.32.8 into 10 to the power of minus 9 meters. Power emitted is given by P is equal to 9.42 milliwatts. That converting into watts, we get 9.42 into 10 to the power of minus 3 watt. We know frequency nu is equal to C by lambda. That is equal to 3 into 10 to the power of minus 8 divided by, given lambda is 632.8 into 10 to the power of minus 9. So, frequency is 4.74 into 10 to the power of 14. E is equal to h nu. H is value of h is 6.63 into 10 to the power of minus 4 into nu is 4.74 into 10 to the power of 14. That is equal to 3.14 into 10 to the power of minus 19 joules. Momentum P is given by P is equal to h by lambda. That is equal to 6.63 into 10 to the power of minus 34 divided by 6.32.8 into 10 to the power of minus 9. That is equal to 1.05 into 10 to the power of minus 27 kg meters per second. Therefore, P is equal to N into E. Therefore, N is equal to P divided by E. So, putting the values, we get P is equal to 9.42 into 10 to the power of minus 3 milliwatts power. This P is power divided by 3.14 into 10 to the power of minus 19. That is equal to 3 into 10 to the power of 16 photons per second. Velocity of hydrogen atom is equal to momentum divided by mass. So, momentum we have calculated as 1.05 into 10 to the power of minus 27 divided by mass, we know 1.673 into 10 to the power of minus 27 kg. Hence, its value becomes, velocity is equal to 0.63 meters per second.